Hi, my name is Chad. I'm a CFI in the Seattle region, and this YouTube video is about Skew-T Log-P diagrams and the Ruck Soundings website, rucksoundings.noaa.gov. And this YouTube video is for general aviation pilots and how to use and read a Skew-T Log-P diagram and what kind of information that can tell you about flight planning purposes and also weather prediction. And then also we'll go through how to pull up different soundings for your flight path that you would be taking and what you could potentially expect. So I'll give you guys an overview of what I'm going to talk about. Obviously, what is a Skew-T Log-P diagram? I might just call it a Skew-T diagram. You can see a Skew-T diagram over here on the right. We'll talk about this diagram and demystify everything that's, or most everything that's in this diagram. We'll talk quickly about how they're obtained. I won't go into a huge amount of detail on that. I'm not a meteorologist or any official data collector on those items, but we'll just chat quickly on roughly how they're obtained. But what we're really going to talk about is what can I learn from them. And I put an asterisk on it. There's a lot that you can learn about them and what kind of information they can provide and what you can glean out of it. But during this video, I'm only going to cover determining cloud bases and cloud tops and how you can predict those for your departure and route and destinations on your flight. And we'll go through some examples to explain how we're determining cloud bases and cloud tops. So again, let's just talk about just weather information real briefly. Basically, you can look at it two things, or two ways in my opinion, the present and the future. So the present, obviously we have METARs, PIREPs. You can look at a webcam. I won't talk about each one of these bullet points. But then you also have future, TAFs. Everyone looks at TAFs. We can look at SIGWICs right here in this lower right corner. This one's incredibly busy, it seems. We can see what in the future, what our weather would look like, either IFR, marginal VFR, turbulence, and such. And then for IFR pilots, especially in the Seattle region, the present and the future are the SIP and FIP forecasts for icing products. But what I want to talk about with this is some of this weather information, especially graphical air emits. They're pretty general. If you look at some of these graphical air emits, the coverage is giant. And a lot of times they're a little too broad. The weather in Seattle is likely even under the same, if you have the same graphical air emit, you're going to have different weather in Seattle than you would over Moses Lake or like your Freda type area. So I feel like graphical air emits are just a little too broad. And I prefer to look at other items to see what my weather is going to be like, especially adverse weather, other than an air emit. Somebody can correct me if I'm wrong on that, but I just find it's too coarse of a brush, if you will. Okay, before we go into a Skew-T diagram, I'll just talk very quickly about data collection methods for Skew-T. Apparently there are multiple sites where we still launch weather balloons. My understanding is twice per day. Down here on the right is roughly about the areas where these weather balloons are launched. And when these balloons go up in the air, they have sensors called radio sounds or ray wind sounds, if you can say that properly. And as these balloons go higher and higher, they record pressure, temperature, relative humidity, winds aloft, things that are typically of interest for obviously weather purposes, but even on the GA side and piloting side, our purposes. These balloons can get pretty high. If you look up, you can look up an individual balloon's report. I've seen them as high as 40,000 feet. They may go higher, I'm not sure. But it's how a lot of these Skew-T diagrams can get generated based off some sensor going up in the air. My understanding is the data collected from these balloons, where you can look them up individually as a standalone, but they also provide information for some computer models that allow us to kind of anywhere where there's a METAR. My understanding, if you have a METAR at your airport, then you can get a sounding through an interpolative computer model for your local region or wherever you're going. So as long as you have a METAR, you can generate a sounding. And again, down here, the graphical representation of the weather balloon data or the interpolated computer model data is what's called a sounding. Okay, so we'll just get right into a sounding that's shown here, and we'll just decode piece by piece of it, and then we'll get into some examples. So the first thing we'll do, we'll just talk about the sounding here is basically, and apologies for this little thing, it'll come up every once in a while based on my Google Slides. But a sounding, we can look at it just like a piece of graph paper that we've had in high school or anything like that. We've got the vertical axis here and the horizontal axis. We'll talk about the vertical axis first. The vertical axis is your altitude, essentially, so pressure over here. So it expressed in millibars. So approximately 1,040 millibars is sea level, and then we reduce pressure as we go up in altitude. If we look on the right side of the vertical, it's also expressed in altitude, only this time in pressure altitude, so something we can all relate to maybe a little bit more, 1,000 feet, 5,000 feet, and so on. There's 15,000 feet that I've got in the box. When we go across the horizontal axis here, you can see tick marks, -10, 0, 10. These are actual temperatures in degrees centigrade. So this big red line or red arrow that I've got here is essentially the freezing point. So everything to the left is freezing, everything over here to the right is above freezing. So another interesting thing is to note, especially with expressed in pressure in millibars, as we go higher and higher, you can see the distance of 100 millibar is getting bigger and bigger as we go up. And that's because air, as it comes down, is compressing on us. So if we're up in space here, outer space, and we can start coming lower and lower, more of that air is compressing down on us. So as a rule of thumb, if we're at sea level, which is about approximately 1040, if we go up to half that value, which is 500 millibar, that equates to roughly 18,000 feet. So if you'd like to think about it, 18,000 feet is approximately half the quote-unquote thickness of the atmosphere when compared to sea level. So further decoding a sounding, so we said again, vertical is our altitude, either in millibar, or we can look over at pressure altitude. Horizontal is temperature. Then what we can look across here is when we do generate a sounding, you'll see we have a red line, squiggly line here, and a blue line. And no surprise, I've already got them labeled. This is our temperature, and this is our dew point, and what our temperature and dew point are doing as we increase in altitude. So we can see here, this is a Seattle generation back in March 12th of 2019. Quite a bit difference between 2020 and 2019, obviously. But you can see at roughly 1,000 feet, we've got a temperature of approximately 5 degrees centigrade, so we're about halfway between 0 and 10, so 5 degrees. But as we come up in altitude, so say we get to roughly 10,000 feet, we are, looks just so happens, we're about -5 degrees in temperature and also in dew point. So that's how we're reading here, temperature and dew point as we go across, as we ascend in altitude. Okay, so further decoding a sounding, when we go into the Java tool, what we can do is we can click anywhere along this graph here, but typically you want to click right where the temperature starts. And what it'll do, it'll give you a magenta line here, and what it does is it gives a theoretical lapse rate of a parcel of air. So if you remember in the private pilot or commercial days where we talk about a lifted parcel of air, and we're all kind of taught that it's about 2 degrees centigrade per 1,000 feet as we ascend, but in reality, those lapse rates change based on if the atmosphere is quote-unquote dry and moist. So we'll talk a little bit about that here a little bit later, but what I wanted to show is the fact that these other lines that are making things pretty busy, we have the blue here. This is the dry adiabatic lapse rate, so you can see them all along here. And then we have the darker line along here, the moist adiabatic lapse rate. You can see them all along here. And then if I can get this thing to go away, I'll pull away for a second. Then we also have the dew point lapse rate that you can see as small lines here. Okay. So what we can do is if we have a temperature here and if you want to assume a certain lapse rate, in this case it dries 3 degrees per 1,000 feet. So as we climb up, we lose 3 degrees per 1,000 feet, but our dew point reduces by approximately 0.5 degrees per 1,000 feet. And these two, since this one's decreasing faster than the dew point, they will hit eventually. And that's where we would say the temperature and dew point theoretically are the same. And this point is called the lifted condensation level. So we'll talk a little bit more about this in some subsequent slides. But I've got to get started somewhere with an introduction to everything. And then finally, with the sounding, you will also get wind information. You've got what they call apparently a hodograph, which best I can tell is looking at winds from looking straight down like you're in the space station. But a far more useful side is looking at its side of winds aloft. So as we go up in altitude, you can see graphically how our winds are doing, where they're coming from. They're coming from the southwest, and then also the wind barbs here. You can also get graphical information with wind as we're starting approximately just above 0, and then we hit 50 knots here, but we all recognize that wind barb for 50 knots, and the max it's looking is approximately 75, 80 knots here. So along with temperature, dew point, we also are getting winds aloft as we go higher and higher. So it's kind of cool, kind of neat to see that kind of information. So a single sounding can provide insight to the following. It can provide insight to where our cloud layers are going to be, both the bases and the tops. And we're just going to talk about that in this video today. But it can also give us icing potential. It can tell us how turbulent things are going to be. Also tell us where turbulence isn't going to be. And then it can also show convective activity, so thunderstorms or just light convection that could be associated with turbulence. So let's just get right into predicting clouds. But before we get into the Skew-T diagrams, let's just talk about what Advisory Circular 00-6B says about clouds. So it says a cloud is a visible aggregate of minute water droplets and or ice particles. So what we see here is an aggregate of minute water droplets and or ice particles. And this happens when, visible moisture happens when an air mass can no longer support the moisture that's in there, and it condenses. Okay, so as we increase in altitude, the surrounding pressure will decrease, and with that, we're all taught that we lose temperature as we go up in altitude, because as the air expands, it also cools as it expands. And on the way up, it cools at approximately 3 degrees C per 1,000 feet, and the dew point is going to drop at about half a degree C per 1,000 feet. And since they come at different rates, the temperature will eventually, for a higher temperature and a lower dew point, which is the case always, temperature will eventually meet up with the dew point. And that point, like we spoke earlier, is called the lifted condensation level. And right there is where the air is saturated and likely where you'll get a cloud. So when you hit the lifted condensation level, then temperature actually decreases at approximately 2 degrees C per 1,000 feet, and the dew point is essentially just along for the ride with the temperature. So that's what you get from the advisory circular. That's what you get from a lot of your bookwork. But temperature and dew point, they decrease at different rates, and when they finally meet, that's the point where we say there's probably a cloud. We see that when the temperature and dew point are right on top of each other at an airport, and it's probably foggy, or definitely foggy, depending on when the temperature and dew point just started to meet, and we can say there's probably a cloud there. Okay, now that we've basically breezed through the clouds and lifted condensation level, we'll dive right into the Skew-T diagram and see what we can glean out of it. So this model was out of Phoenix just recently, and I picked this one just because we can see some pretty large variations in temperature and dew point. So Phoenix, it looks like it's pressure altitude, its field elevations were roughly around 1,000 feet. So as we can see, when we look at the temperature and dew point at Phoenix at this time was approximately, I'd say, around 23 degrees C. Its dew point was about 3 degrees C. And so that's a pretty big temperature to dew point spread, right? So highly likely there's not going to be any clouds. And then as we go higher and higher in altitude, you can see the temperature and dew point spread, so the distance between these two gets closer and closer. So instead of approximately 20 degrees difference, now we're getting into in the order of less than 10 degrees. Okay. So what's interesting here is not only does they get close, but you can see the dew point really takes a dive off to the left here, and it goes way low. So from anyways, we just crossed about freezing here, and then it went down to minus 40 degrees centigrade. And what's interesting about that is the fact dew point is the point where we have to take, once we get to this level, we have to cool this air all the way to minus 40 degrees C to get any condensation to happen. Another way to think of it is it's kind of like a sponge. The lower the dew point, the harder you have to squeeze that sponge to get any water to drip out of that sponge. Okay, so when the dew point's higher, we don't have to squeeze as hard to condense, if you will, or squeeze out moisture out of that sponge. But when we get here, there's a lot less moisture, so we really got to squeeze hard to kick out any moisture. So as the temperature and dew point come here, then all of a sudden we just got effectively much drier. So what likely happened here? We likely condensed out a cloud. And this is also predicted by the lifted condensation level, as the temperature would come up theoretically at the dry adiabatic lapse rate of 3 degrees C per 1,000 feet. And the dew point, which you can see in this line here, theoretically would come up in here on this slope, and they meet right here. And that predicts that this is where a cloud base would be. So between the fact that we've got a closer temperature and dew point associated with a massive drop-off in available moisture, we can probably say, yeah, there's probably a cloud here. So we'll go to the next page here and see what the associated PIREP was. So we can see for the given time, the 25th, at 0051 Zulu, we had few clouds at 8,000 and scattered at 25,000. And also of note the temperature and dew point, 24 degrees C and 2 degrees C. So what did we say earlier? Temperature is 24, dew point is approximately, I was saying maybe 3 or 4, it's about 2. And then let's go back to we said 8,000 for a few clouds. So if we go in between here, 8,000 is roughly across here. And we can see right in this level, there was clouds roughly at 8,000. Now, I also said there were some clouds at, let's go back, 25,000. We'll go across here, and we can see the temperature and dew point getting closer again here. So you can suspect that there was likely clouds in this area. Now, when things get really cold, the standard temperature and dew point rules don't necessarily apply because now we're not worried about dew or worried about frost. But it's still, if you see the temperature and dew point get close to each other, even these higher altitudes, likely there would be a cloud. So interesting to see here. Just want to give one kind of a quote-unquote easy one to start off with. But we see the fact that the temperature and dew point are getting close to each other. That's a first sign. And then also associated big dew point drop is another sign. All right, so let's work on another example here, this time without any annotations to the graph. This one's going to be for my old hometown, Kansas City. We're going to see a vastly different picture here. This time we're starting off with a much closer temperature and dew point spread, and then we're actually seeing a temperature and dew point actually on top of each other. So if we click that line, and I'll show that later, and when we actually do some examples, we can see where the temperature and dew point would theoretically meet at the lifted condensation level is very low. And the temperature and dew point here are staying right on top of each other, and then they start to diverge. So what's interesting about this is at that divergent point, we can say, okay, well, likely in this also we have an associated drop with dew point slightly. It comes back in and then comes back out. So if I was to look at this planning a flight, I could say, okay, I plan on being probably in the clouds at least until approximately 7,000-ish feet. Okay. Now there's a chance I'd be clear at approximately 6,000 feet, but it might have some layers in this area. But highly likely once I get above here that I'd be clear of the clouds for the remaining of the climb if I was going up to, I don't know, anywhere between 10 and 15,000 feet. So for GA pilots, I don't see us really going that often higher than 18,000 just for the differences in required oxygen systems. So again, we're looking for temperature and dew point on top of each other. Then we see the divergence. So I would say approximately 8,000 feet, I'd be clear of the clouds. So let's see what the PyRep says for it. PyRep says there's overcast at 3,200 feet. Okay, I could believe that. I would say maybe, I would almost say 2,500 feet. But then their tops were at 4,000. So approximately 4,000. There's 5,000, so maybe just about in this area is right about where they diverged. Okay, so I said probably might get a little pocket here, and then definitely we should be safe up in this area. Now there's one more tool you can use to supplement this piece of information, and it's the infrared satellite. So what we can do is we can look at these temperatures in this area, and then we can look at the infrared satellite to see what the cloud tops are based on their temperature. So let's just say, let's just look at how they said the tops are at 4,000 feet. So 4,000 feet is approximately 5 degrees Celsius, maybe 5 or 6 degrees Celsius. Okay. So we can look, I've got the next slide here, the associated infrared image at that time over the Kansas City area. So I've got the Kansas City area, it's that white dot. And we said it was approximately plus 6 degrees centigrade at that observed pilot report. And we can see we've got this reddish burnt orange color here, and we can see where that is associated with in temperature. So I would say between, yeah, roughly about 4-6 degrees centigrade is here, and that shows up here. This is a layer of anywhere between, I'd say at the best, or and locally, the worst they would get is roughly 0 degrees centigrade. So we could say anywhere within this realm, the lowest temperature we see is 0. So we can go back to this sounding of the local area, and the lowest we saw was roughly 0. So 0 is associated with approximately, now we talked about up in here, approximately 9,000 feet. So locally, you can see Kansas City, let's go through here. Kansas City is also going between anywhere from 0 to darker color, maybe say 12 to 16 degrees. So, oops, go back one more. There we go. So anywhere between 0 and approximately 12. So anywhere from a high cloud to essentially maybe all the way down to the surface, no cloud within that region. So if you're doing a flight around Kansas City, I would say if you're going up north, I would say you'd be getting out of the clouds fairly quickly. If you're going to the east, you'd probably be in the 0 degree, which I would say is roughly the 9,000 foot tops of clouds. So if you want to get out, clear the clouds, and we're going east in VFR, then, well, I guess we couldn't go VFR, so IFR. If you wanted to go above to 11,000 feet, then you would likely be clear of the clouds. So we'll do another example. This time it's in the South Bend, Indiana area, and kind of similar to Kansas City. We can see that there's a temperature and dew point convergence pretty close to the field elevation. But then you see a pretty rapid divergence between temperature and dew point. So I would say with even a little more confidence that we would likely be clear of any clouds once we got above approximately 4,000 feet. And then as we come up into altitude, there's potential we would hit some clouds at the 14 to 15,000 foot level, and then higher than likely that we would hit above 22,000 up through potentially 34,000 feet in these areas. Again, when we get colder, the temperature and dew point, if they're within approximately 4 degrees of each other, likely there's clouds as when we get pretty cold. So it's a little bit different rules than when we're down in typical GA, especially non-turbo turbo-driven pistons. Then different rules apply. But I would say as we come through here, 4,000 would be clear, and maybe some clouds up higher. So let's think about that and say, okay, well, let me look at, let's look at the actual PIREP for that area. And it looks like for that approximate area, there is 0 icing, and we'll get to that in a second. And there is overcast at 3,200, which I could get on board with that. And the tops were roughly about 4,300, and I can get on board with that. There's no other observation about anything higher, but they also said icing was negative. And that's an interesting thing here too. I said we wouldn't talk about icing, but we'll talk about something real quickly. As you can see, we talk about the temperature drops anywhere between 3 and 2 degrees C per 1,000 feet. But that's just a rule of thumb. It's not necessarily always the given. So we can actually see that temperature reduces as we go up, then it's actually increasing as we go up, and then it finally goes back to the freezing line back at roughly 7,500 feet. So we would hit freezing at approximately 3,500 feet, but if we actually climbed higher to 5,000, maybe 6,000 feet, we'd actually be out of the ice if there was ice in this area. So this is another really valuable thing to see kind of what's going on in the weather as you climb. Like I said, sometimes reducing altitude actually can get you more in trouble than if you climbed. So this is a neat piece of information to see the local area, what's kind of going on. Another kind of hint that kind of goes on where cloud tops or bases could be is associated winds. So you can see here there's a wind shift. Winds are coming roughly from the southeast, and then they do a pretty dramatic shift from southeast or a little bit more easterly to more south-southwest. A lot of times if you see a wind shift like that, there's likely a break in the clouds or a start of a cloud or something along those lines. And that proves to be true here. So let's look at the infrared satellite and see what we can see if this shows up down here with associated temperatures. I put a black dot here where South Bend approximately is. And we can see the color codes here were pretty blue. And these blue colors are in the -40 to -36 range. But we were saying our altitudes were going to be freezing to maybe mildly above. So what's that telling us? Well, the infrared satellite can only see what's in front of it. It's kind of like if you put your right hand in front of your face and then put your left hand over your right hand. Now you can only see your left hand if you can follow that. So the infrared satellite's the same thing. It can only see the first thing it sees. And in this case, it's something really cold and likely something a lot higher than where we are. So if we go back and look at the chart, so it's seeing something roughly along the lines of, we'll call it just -40 degrees for simplicity. If we track -40 degrees over here all the way up, likely the cloud tops are in this realm of somewhere between 25 and 30,000 feet, maybe even higher. And that probably makes sense by the fact that we're seeing a close temperature and dew point spread all the way through here in these flight levels. So the infrared satellite doesn't necessarily give us the rock solid picture like it did in Kansas City, but it still gives you what's going on at these upper flight levels. So we can still try to be fairly confident with what we see in this area. If there's no icing, excuse me, no icing PIREPs or even the SIP and FIP, if they show no icing, likely they're using some type of model like this that's showing there's not any temperature and dew point or visible moisture that we'd be attacking flying at these altitudes. So the infrared satellite's a pretty useful tool, but it's not useful if there's some clouds in the way of our line of sight coming down through and coming where we're flying. So just be mindful of that. So with some basic examples out of the way, let's go to the rucksoundings.noaa.gov site, and we'll just do some examples, quote-unquote real-time, or real-time as I record this, and hopefully this makes a little bit more sense. All right, so we'll get into some examples and how to use the Ruck Soundings tool from NOAA. Immediate thing you'll notice is when you get on here, it looks like a late 90s, early 2000s type website, just the way it is. So when you log in, or not log in, but rather get onto the website, essentially what you'll do is you'll go down to this table in here. There's a lot of things that are selected by default. I never really get into these different, some of these items, I just leave them as default. So we'll get into these different rows here right now. So initial data source, the OP40 is the typical default data source that you'll get from a Ruck Soundings. It's I don't really know a lot. It's difficult to find information about these different data sources. I do know that this one right here is weather balloons. If you can find the right weather balloons, you can get that raw data from a balloon. But this is my understanding, the computerized model of the different areas. If you have a METAR, you should be able to pull up a sounding using OP40 and then putting in your METAR location. Valid time, so we can start the valid time, either the latest models that are ran, or we can uncheck this and put down certain times and dates and times that would be of interest to us. So you can go back in history a little bit, or you can go into the future a little bit to say, I only care about a certain amount of time, like 3 hours in the future. But another way to look into the future is just to say latest, and you can say I'm interested in 4 hours. In this case, it's already got some pre-populated things in mind. I'm interested in 4 hours in the future. This right here is another default that I never really mess with. You can look across here. I don't have a lot of information on this, but I just keep it as default. And then sites, what we'll do is we'll look at certain sites. So we'll just I'll pull up Seattle right now. So you don't have to put the K in it. If you put a K in there, it won't work. So SEA, press enter. And you can see, so the latest model generation, which was 1600 Zulu across here, then every hour for 4 hours was selected. So 16, 17, 18, 19. And then the associated weather that's coming through here. Now, since we're just talking about how to use the tool just real quick, as opposed to looking at the data, you can also say, okay, well, I'm interested in another airport while I've got it up, so I can click Load Soundings. In this case, I'm interested in, say, Portland, PDX. The same latest start time, 4 hours, op 40. And the shortest, the same search terms, if you will, as what we did for Seattle. I can say load. Now it loaded PDX on top of Seattle, so we can look at PDX 16, 17, 18, 19. It looks pretty much the same as Seattle, so go across. Well, another trick you can do is you can press Seattle, for instance, here, and hold Shift, and say for some reason my flight's going to take 2 hours to get there. I can press Shift and press 18. Now what it does is overlays the two, so you can see now in the magenta is PDX, and Seattle is the black, and you can see how the lines overlap each other. So you can see it's not a big change in weather as we go down through that area. So we said there's not a big change in that area between 1600 Zulu and 1800 Zulu between Seattle and PDX. What's also interesting is the temperature and dew point for both these areas are right on top of each other all the way, at least until, they only start going about 13,000 feet until they finally start to diverge. So this one's a tougher one to analyze based than other examples I've shown. Let's see what we can get out of it based on that. When this slow divergence happens, this is where I try to rely on the satellite images, particularly at the infrared. So let's see if I got pulled up here. So we said between 16 and 1800 Zulu. That was the weather. So the latest I have right now is 1651. I'll look at, I know Lewiston kind of zooms in on that area. So we got the Seattle region in here, and we've gotten the Portland region down in this area. So within this area, we're at worst case scenario, we're getting into the yellow-green, and yellow-green is anywhere between about 10 to, we'll call it worst case, about 22 degrees C. So between 10 and 22 degrees C is where the infrared seeing cloud tops. So 10 and 22 in our heads. We'll look over back here, find 10. So cloud tops would likely be somewhere around 7,000 feet. And we said 22, so quite a bit of ways up to 14,000 feet. So within that realm, if you wanted to absolutely be safe, I would fly somewhere higher than 14,000 feet to be out of the clouds in the area. That's not very practical for people without some type of Fiki airplane, but that's how you would analyze this type of situation where you're seeing not a big divergence down low or anywhere until you get fairly high. So I just want to show you how to read the chart even with some weird weather patterns here. So the previous example that I spoke of was Seattle to Portland. It didn't really apply to us, a lot of GA people. We don't have Fiki typically. This was a very cold and icy trip, likely, if we were on a GA plane. Still think it's worth looking at to see all sorts of different models to really understand it. But let's try to find something that's a little more applicable to what a standard GA pilot would be willing to encounter Fair warning, I did look ahead at a PIREP that would be more applicable to us, and it's in the West Virginia area. So, but I'll show you. It's not just because I already know the answer that it's just because I know the answer I know how to come up with the questions. But I'll show you why that PIREP and the RUC sounding those all align here. So, in the West Virginia area, we can see how this is a little more applicable to us. We look like we have a cloud tops at roughly anywhere. We're starting to get in the 0 to -4 range. So again, there could be an icing for us, but definitely not Mondo icing, if you want to call it, over in Seattle and Portland area. So let's say we wanted to avoid some clouds, or at least know where they are in this West Virginia area. We can already look at the temperature, and we can say, okay, it's roughly anywhere between 0 and -4 maybe, or somewhere in this realm. And then we'll go ahead and we'll take a look at the RUC soundings for that area. So KCRW was the area in that realm. So let's look number of hours, same thing as Seattle, Portland. Do 3 hours ahead, the latest model. CRW was the region. And on this infrared model, let's see, we have 1700 Zulu. So we'll look at 1700 Zulu. And just to confirm, it does have CRW in our area. And we can look and we can say, okay, as we come across here, not until about 4600 can we have any chance of probably getting out of the clouds. And if we look at the a little bit before, you can see how the trend is the temperature and dew point are actually getting bigger and bigger from each other. So between 16 and 17, about 4600, I wouldn't say until you get there. If you always want to be a little bit safe, go a little higher. And if you really want to be conservative, you can say, okay, I know by the time this really takes off, the dew point really starts to get dry and cold. Very conservative would be 7,300 feet. So anywhere between 5 and 7,300 feet, you know you would be in the clear. Now for icing purposes, you'd probably be in pretty good shape by the fact that if you're at 5,600 feet, you're at least at 36 degrees F or 2.4 C. And then by the time you get higher in the freezing range, you should be both freezing but clear above the clouds. So between these two areas, there shouldn't be an icing risk if you're coming through in here. So let's take a look. So it looks like the pilot report was overcast at 1300 with tops at 5,000. The time was 1600 Zulu. So let's adjust that back to 1600 Zulu. Not a huge change. And so in the CRW region, we were saying approximately tops around, oops, sorry about that, 1600 Zulu. We were saying, yeah, anywhere 5,000 where things start dropping. If you want to be really conservative, go a little bit higher. I would say even 75, but this is where you're trending better. You're safer higher if you're worried about being in the clouds or icing. So that pilot report was reasonably accurate. And it's also backed up by the fact we have an infrared of worst case scenario, maybe a 0 or so, maybe a 4-degree temperature, and that shows up roughly in this realm. Well, that's all I've got for Skew-T diagrams for cloud bases and tops. Let me know if you like this. Like I said, I hope you did. This is pretty casual. I'm not a video producer by any means. This is the first video I've done, so give me any mercy on production value and my overall tone and speaking and everything like that. So hopefully it was bearable. So I encourage you to try this out at home to supplement your typical weather briefings and see if it matches your expectations. So you can do it at home where you can look at PIREPs to see if it matches the PIREP, but then you can also do it whenever you kind of get back to flying more. Um, Use it to supplement your typical weather briefings and say, okay, that actually made sense, or I predicted cloud tops and bases to be at these levels, and sure enough, there they were. It's not going to be exact, but it should be within plus or minus, sometimes as good as, plus or minus 500 feet or even better. So if I get enough positive responses out of this, I'll make the videos for the remaining items. I crossed out cloud layers. Make videos for the remaining items below, and then maybe I'll get a little higher production value going on in these. So I'll also list a few other websites, references, and then also there's an app called Skew-T Log-P that maybe makes pulling up these diagrams a little bit easier for flight planning purposes. So again, hope you enjoyed it. Please leave any constructive criticism, and we'll see you later.